Okay, our last day of chapter 16. So Monday is going to be the exam, and then Wednesday just plan on starting chapter 17. So come with the bold words, and that's for chapter 17.
Oh, sorry.
And we've been doing this for how many weeks?
Okay, well, can you make sure you count them? I wrote them on this homework assignment.
Okay, so where was I? So Wednesday, whether we do chapter 17 or not, I'm not sure. I mean, I'll figure things out. At least this way we're ready to go. And you can count it as a point, some points. So what I wanted to talk to you about is that this upcoming exam, with my super long amount of experience that I have doing this, I have a bad feeling about this upcoming exam. Because when I just finished it about, I don't know, 10 minutes ago or whatever. And it's 90 points total, but 70 of it is conceptual. So that means there's just two problems.
Is it finding the force constant?
So
Find a case and I can do that. It's a solid 20 points.
It sounds familiar, actually.
Well, don't change it.
But so there's two problems, and because I was just looking through and I looked and found my two favorite problems, and that's what we did. So there's only two, but so 70 out of 90 is all conceptual. So how do you study for this conceptual stuff? And what I did, I just got on this kick, and what I did is I took almost every single diagram here. What I did is I copied it, pasted it into the exam, and then did some things to it and asked you some questions on it. So all 70 of those points, pretty much all of them, there might be a few that's just a conceptual question that has nothing to do with the diagram, but almost all of them do. So that's what you should focus on, are all these little diagrams and what each one means. And that's because that's what I did. So for example, if you take a look at this very first one, right? It's very easy. Just imagine what I can do here. That's probably would give you some insights into what's going on. See what I can do. I can draw a text box. Come on, draw a text box, right? And I can put it over whatever I want.
On like label?
Right? So that's the sort of thing that you could be asked to do. So recognize those are the powers that I have in messing with these diagrams. So when I say messing with these diagrams, it doesn't mean that everything is going to be there. Certain things that could be missing, and then you got. So, but the point is if you understand the diagram, you can fill in whatever I covered up. Now, I'm not saying, what are these nanometers? You got to memorize this range. No. The concept here is this is what energy and this is what energy. Higher, it goes from high to low, or is this going from low to high? This is going from low to high. So what are the colors in low to high? That's what you have to know, right? Look at the radio waves corresponds with this nuclear magnetism, right? Microwaves corresponds with rotation. Infrared corresponds with vibration, right? So these are the things that you should know and that I could ask you about, okay? So I kind of gave you some hints as to the questions that I could ask you on here. If we, I don't remember what this was even about, these two. What was this even about? Stokes radiation. I don't know about that one. What was this 16.7 and 16.8? I don't even remember what that was. Oh! So there's some stuff missing in this. I have to look at my notes. What the hell is this? You go from one to the other, how? Fourier transform. technically there's a -1 over there, so it was inverse Fourier transform. But Fourier transform is good enough. That's the answer, right? You go from some signal that's changing with some physical parameter, right? And then you get the frequencies that were in that signal. Okay, here's Raman spectroscopy. It's a Raman spectrometer. Why would they use a laser? That's not really part of the diagram, but I guess it's the concept. Why would they use a laser? Because what is Raman? Scattered light. This light has to be scattered. And if you want to see scattered light, just shining a flashlight through something, you're not going to see a whole lot. And since you're after scattered light goes everywhere, right? But why do they observe at 90 degrees? Why would they do that? Nothing really magical about it. It's just practical. Why would that be practical? It's pretty much where you get the least amount of that laser light. Right? They're trying to avoid this incident radiation. So you definitely don't want to have it over here. But it's pretty much just convention. You can have it pretty much at whatever angle you want. But you just definitely don't want to have it over here. There's
Want the least amount of incident radiation?
Yeah, you're just trying to avoid the incident radiation, I guess. There's not a whole lot I can ask there. How about this one? So what we're going to do, we're going to start with this one. And we're going to go around. We'll start with Mel. And Mel's going to tell us everything she knows about this.
Wait, I know something. Start with me.
Okay, we'll start with Al. We'll start with Al on this one.
Okay, so at the top, that's an incoming photon. It's the electric.
Oh, wait.
Oh, I'm gonna write this?
Well, no, don't write it. Because you say at the top. Nobody knows what you're talking
How do I
about.
use this?
Oh, laser. Let's go laser pointer. Where's my laser? I have a laser pointer. Yeah, but I don't know where it is. I'll be right back. Hang on. What color do you want? Red, purple, or green? Okay.
Okay. So up here is an incoming photon. This right here is the electric field. What else did I write? This is the outgoing photon. This is the increase. This is an
Wait. Before you move on, stick to that same one.
Stick to the just
Why did? No. Show me the outgoing photon again.
right here.
Yeah. Well, really, it's that whole thing, right?
Uh-huh.
That whole thing's the outgoing photon. Why is it bigger than the incoming one?
Oh, I didn't write that down. It changes in amplitude?
Yeah.
Oh yeah, amplitude is increasing. No change in frequency.
Yeah. And what else didn't change? Starts the P. That sounds like F.
Photon?
The F. They're in sync. The
Frequency. What?
phase.
What is it P?
The
Oh,
phase. The phase. The
phase.
phase didn't change,
No change in phase.
right?
Oh.
So so that's what they call, what's the process you just described?
Is this absorption?
It's called,
No.
you have an incoming photon, then it comes out even bigger.
Stimulated emission.
Stimulated emission. So you're describing stimulated emission. Okay, good. Keep going. And that's the building of a what? That's the inner workings of a what? You're using it?
What?
You're using it.
Me?
And now it's your turn.
That's the inner workings of a
Laser.
laser, which
what's the
stands
difference?
for.
Light amplification, stimulated emission,
Resonator.
resonator.
Okay, keep. You don't want to finish your diagram? You're handing off the thing already?
Oh, yeah.
Okay. So what else can you say about it?
Energy increases this way, going up.
Okay. Yeah.
That's all I wrote down.
Okay. Pass the wand on. Is there anything else you can add to that, Mr. Mraz?
This is ground state, this is excited.
Yeah.
She said everything else. I wrote down too.
Well, there's some things you didn't pick out yet. You haven't talked about everything. There's two processes you haven't talked about.
Oh, the stimulated absorption.
Okay, you know, stick to one, stimulated absorption. So you already identified ground state and excited state. So what is this?
So another incoming photon?
Exactly. All right, does that make sense?
Mm-hmm.
So this is called, you have an incoming photon, goes to excited state, that's called?
Absorption.
Yeah, absorption, but we're supposed to technically call it stimulated absorption. It's kind of crazy, right? We always just call it absorption. Anyway.
From excited to ground, it's called spontaneous emission.
Yep. What is this?
Another photon.
Another photon being emitted, right? Is this emitted? Whoa, what the heck is wrong with that one? This one you can't see. Jeffrey, is this emitted photon the same as this incoming photon? Now, when I say the same, what am I talking about?
Like the amplitude?
The actual physical same one?
No, like the same energy,
Yeah. Now, when you say energy, how do you characterize that?
frequency,
You could say same frequency. You could say same
color,
color. You could say same.
phase.
Amplitude?
Well, phase, no, because because this is gone. He starts. They're going to be out of phase. Now you could talk about amplitude, right? But I don't know if they're going to be in the same amplitude, right? Because this is instant. This is probably huge. This one is probably small. So if that's one area where they could improve on this diagram.
Yeah, that one's
Make
good.
this incoming photon really small, right? Make this one really big. So you want a lot of intense light. And then, you don't see much because most of that energy doesn't go to emission. Most of it just, it turns into heat. Remember that? And instrumental, we talked about that. Internal conversion. Anyway. So that's all of them. What were the? That's an instrumental analysis question. I don't think we ask that here. Okay, so that's good for that one. There's another one. Okay, pass the torch. You didn't really. Well, okay, pass the torch. Jeez, give it back to Mraz. He didn't answer hardly jack.
Take it back.
What are you talking about?
Okay,
He said everything.
say what you know about this one.
I ain't read a whole lot.
Well, just describe it. You don't need to say what's in the notes. Just describe what's going on here. It's a plot of what versus what. What's going on?
Frequency versus absorption. So I wrote down helium atoms approach the detector away from the detector when it emits.
Now, hang on. Before you get into that kind of stuff, frequency of what? Absorption of what? What are they talking about?
The atom.
frequency of the atoms? That doesn't make sense.
Are they detected? Does it do with Doppler effect?
Does it do with light? I don't know. It's a molecule, isn't
Okay.
it?
Keep go-
I think it's a molecule.
So this is frequency of the molecule? What is this? How do you get this plot, Jeffrey? He hasn't had instrumental. Mel, you've had instrumental. How do you get an This is absorption. How do you get an absorption signal?
Put in UV.
Put in a UV, great, okay. What do you got going on there?
The light passes through the cuvette.
I'm excited.
Okay, you get light passing through a cuvette.
The molecule is excited in absorption spectrum.
So the light gets
Inside.
intense? You just said that it got absorbed and goes to the excited state or something.
Where the light passes through the cuvette, the molecule gets.
Light passes through cuvette, the light gets, as it passes through the cuvette, the light gets what? Here's the cuvette,
Absorbed.
it gets absorbed, okay. So what is the light over here? Does it all get absorbed?
No.
No. So the light gets what?
Transmitted.
Okay, it's getting transmitted, but you have light here, what's the difference?
Incident light.
Okay, here, this side's called incident, right? What's the difference?
The light not being absorbed passes through.
The light not being absorbed passes through, so what's the difference between those two?
The intensity?
Intensity. The light got attenuated. The guy hasn't even had instrumental. All right, the light got attenuated. Okay. So if you measure the difference in those intensities, take the log of it, you get this absorbance, right? So this frequency is what in this process that you have? You've got your little cuvette, right? Incident, transmitted, little detector. What's that frequency? What's even further in front of the cuvette? You have your little light bulb over here. Then what? Alyssa, then what? You got a little light bulb? Is the light bulb giving out all the colors?
Oh, the gradient?
The gradient. Well, it's called a... Now, this is much more information than you need to answer this question, but you need to see the concept, the monochrometer. It's a wavelength selector. So this incident light, is it all wavelengths?
No.
Okay, what word can you use besides wavelength? Frequency. So what's striking, there you have individual frequencies striking this cuvette, right? And as it passes through, it gets the A word, attenuated. Otherwise, you wouldn't have an absorbance, right? So if this instrument's doing its job, it's only sending one frequency through at a time. We could talk about wavelength if we wanted. Just change this word to wavelength. Who cares? No big deal. Change this word to energy. Who cares? No big deal. All right? They're talking about in an individual, a very narrow range of frequencies hitting this thing at once. And then you measure the absorbance of it, right? The incident over the transmitted, take a log of it, and you get plot dot, 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 right? Oh, this is full of a bunch of dots. Okay. So indicate an absorbance spectrum. And I'm sure this is a gas because everything that we've done on the UV vis and instrumental, did you ever get a spectrum that looks like this on the UV vis? Oh, you got these big blobs, right? They're all solutions. So this is definitely a gas. But it's the same idea, an absorbance spectrum. Okay. So I think you have an idea of now where this absorption's coming from and what this frequency is. So what's going on with the plot? It's trying to show what?
Doppler broadening.
Well, he's trying to show what?
Changing frequency.
Well, here's frequency down here. What's going, they have 3 plots here.
It's the transmittance divided by 3 transmittance times.
No, T isn't transmittance. What's T? What's T?
That's just the temperature.
Temperature. T is temperature. So this is the exact, all they're doing is changing the temperature of that cuvette, of the gas, of the solution. They're just changing its temperatures. All they're doing, then they're doing the exact same over and over again. And look what happens to the absorbance spectrum. So how can you put that in words? How does the absorbance spectrum change with temperature?
There's less absorption at higher temperatures.
At higher temperatures would be what color? Plot here.
Red.
Red, okay, because it's 3 times T. I mean, I agree with that. But if you say higher absorbance, when I think of higher anything with an instrument, I'm thinking of area under the curve. So I see you're right in the sense that you have, it's a lower overall maximum height, but the area under the curve is pretty much the same. So when you say the degree to which it absorbs, not really.
The rate of broadening.
Okay, things are broader. Why? Now this talk comes in. As you crank up the temp, what's the difference with these gas molecules? Now it's important to think of it as a gas. The solution idea isn't going to work because it doesn't work with the solution.
We get excited all over the place.
They start,
Interacting.
yeah,
Colliding.
yeah. Well, you don't want too much collision. That's going to mess up everything here. You want pretty dilute gas. They're going to start. What type of? Yeah, you increase the temperature, motion in general goes faster, more random. But what type of motion are we really interested in? Vibrating, rotating, spinning. What type of motion are we really interested in if we want to talk about Doppler? Yeah, translational motion, right? So these molecules they're moving really fast, either towards the light or away from the light. So it messes everything up. You had this nice monochromator that's sending out exactly 600 nanometers of light, right? It's exactly 600 nanometers. Well, if this damn molecule wouldn't move, it would see 600 nanometers. But it's moving, and you crank up the temperature, so there's even this bigger, wider range of this movement. So these molecules are going away from that 600 nanometers, so it sees redder or longer, redder or bluer.
Away from 600.
Yeah, it's moving away from the light.
So blue.
Think of the sine waves like this, and if the molecule is going towards it, the sine waves get closer and closer, higher frequency. If the object's going away, then the sine wave gets longer. So it's getting redder. So the molecule is flying away from the light source. It doesn't see 600, it sees 610. So it's absorbing now at 610, where it should be absorbing 600. And they could just as well be going towards it. So it doesn't see 600, it sees 580. So it just really broadens things out because of this Doppler shift. So with increasing temperature, really enhances this Doppler broadening. Because this is supposed to be this plot, it's a gas, darn it. This is it. It should be a line. It should be one very thin line because you have one ground state, you have one excited state, boom. That's all it can do. You just jump from this energy to that energy. But according to this thing, no, you can jump from a smear of energies. From this energy to this one. From this one to that one. From this one to down here. All over the place. This big smear of energies is where it's jumping around to. Right? It's almost like this big blob in here. And it's going from here to every single one of those energy states in there. And this blob gets wider and wider and wider. This gets even bigger and bigger and bigger the more you increase the temperature. That's what it looks like. But yeah, that's not happening. It's the Doppler effect. It's false. Right? You make it super cold, and maybe you can get back to this and see one really sharp line. And that energy corresponds to this energy, corresponds to that, between the ground state and the excited state. Right? So it'd be really super narrow. And it might only have a little bit of width due to the Heisenberg uncertainty principle. But so that's the idea behind that plot. How about this? There's not a whole lot to say on this one. This is supposed to be what? Energy levels of what type of transition? Falls under what type of transition? Rotational. Which is in what region of the electromagnetic spectrum? Microwave, right? That pulls you back up to the very first picture that we talked about. And then if you do something like this, dang, those rotational energy levels, I just deleted it, but you had all these rotational energy levels. They were just J. But then for each J, there's M sub J goes from negative J to positive J. You have all these M sub J's. Well, you don't see those. Those don't come into play until you turn on an electric field. So that's what this is about. So there's not really a whole lot to talk about that one. We spent some time on this, though. Okay. Whose turn is it? Jeffrey. What can you tell us about this plot? What's going on here?
Vibration or rotation, right?
Trying to show a molecule rotating. I agree with that.
And that as it's
Is it?
rotating,
Let's stick on this first idea first. Is it being used to describe vibrations? I heard you say vibration earlier. Is this depiction used to describe or help you describe vibrational transitions?
no.
No. We're talking about rotation here. Okay, keep going.
So these atoms on the end,
Mm-hmm.
as it rotates, they're getting forced out.
They're getting forced out.
Or up, where this.
Yeah, I see what you're saying. Due to inertia, right?
Yeah.
Okay. Now, if that happens, is that supposed to happen?
Yeah.
If it happens, we can't do any of our homework.
So no.
What if it happens? If you, like you said, if these guys spread out, if it gets distorted, It's no longer a what? What do they call these things? And we had tables of them to describe their moments of inertia. Rotors. And they were linear or they were whatever. Rigid was the key word. Rigid rotor. If this thing distorts, it's not a rigid rotor, you can't do any of our homework. If this thing distorts, what is present? Starts with an A. May even be in here notes here somewhere. Anharmonicity. Anharmonic distortion. So you jumped all the way to anharmonic distortion. That's not what this thing's trying to say. To me, this thing's trying to say what a rigid rotor is. Rigid rotor doesn't do this stuff. Rigid rotor doesn't distort. Right? At least that's what I'm thinking. Even though you have these big arrows and stuff. Is there anything else you can say about that plot, that picture?
That centrifugal force is wrong. It should be centrifugal force.
Okay, centrifugal force is wrong. It should be centripetal force. Is that correct? So you're saying I can cross out centrifugal and write the word centripetal.
Well, you shouldn't call it centrifugal force before.
Centrifugal force isn't a force. It's really just what?
A movement,
Yeah.
like in a centrifuge, like they settle at the bottom. It's kind of like an action.
Yeah, it's nature. It's starts with an I.
Inertia.
It's inertia. It's what all mass does that. Just keeps on moving in a straight line until it's acted upon by an unbalanced force. Okay, so you mentioned the word centripetal. So you got to cross out centrifugal force, and you're supposed to write what instead? Inertia. Or just write, this is what mass wants to do. And these little balls here have mass. Not a whole lot, but they have mass. He mentioned centripetal force. Where would that be? That's the only force existing in this whole thing. Where would you draw the arrows? Now you have momentum, angular momentum. You can actually do the right-hand rule to figure out and draw a nice big arrow and write an L with a vector sign above it, but that's not a force, that's momentum. Centripetal force. Give you a hint. If you want to take a bucket of water and just swing it around like this, right? You have to be holding that bucket of water. And you're pulling on that handle the whole time, right? Otherwise, it's going to go flying out in a straight line. So the whole time, you are pulling on that handle. So you are pulling on it. So there you go. Centripetal force starts here, goes towards the center. Just like the bucket. It would start at the handle and go up your arm. It's the force necessary to keep that circular motion going in the first place. That's where centripetal force would be. Okay, what could I ask here? We didn't really do a whole lot. What's the difference, anybody, between railay and ramen? What's the difference? They're both supposed to be what type of process? What's going on? Scattering light. They're both scattering light, exactly. So what's the difference? They're both scattering light processes, so why call it two different processes?
One's elastic.
One type of process is elastic, one type of process is inelastic. So what does that mean for the scattered light? If it's an elastic collision, what's conserved? Kind of think of it that way. If you want to go back to general physics. Steel ball, ching! Assuming no sound or heat's generated.
Energy is conserved.
Energy's conserved, right? Momentum's conserved. But if you're talking about light, if energy is conserved, what does that mean? Incident radiation's going in. How do you describe that incident radiation? You could describe its energy, which is its frequency, right? Or color, right? Frequency. So the same frequency goes in, same frequency goes out, right? If it's scattered, that would be an elastic process. Which one do we call that?
Really?
Railay. That's why the sky's blue. Nitrogen. And the size of blue wavelength, they just match perfect. All right, so if you have an inelastic collision, inelastic process, inelastic interaction between this hunk of dirt and this incoming radiation, the scattered light, what?
It's polarized.
Changes frequency.
Changes frequency. It can either change, so there, you can either change,
Can get higher or lower.
can get higher or lower. So pick orange, right? So you have incident orange, it could get scattered out yellow, or it could get scattered out red, right? Or it gets scattered out orange, that'd be the railay. So whether the frequency gets lowered or higher, there's your Stokes and your anti-Stokes. Okay. So anti-Stokes is higher frequency. Okay, Mel, what's this picture have to do with anything?
Well, this displacement's supposed to be vector. So these are going on forever and ever and ever.
Okay, hang on. Vector, to describe what? It's a plot of what versus what, and where are these things coming from?
Potential energy versus displacement.
Okay, and you already said displacement's a vector, but what do you mean? A vector of what? How are you getting this measurement? What is it? I actually wanted to measure that x and make that plot and put a little dot on there.
So we'll use a spring as an example.
Okay, you could use spring as an example. It'd work great. Okay, how could you measure displacement?
How far it moves. So we have the spring, so how far it moves from the potential of 0 going up.
Okay, now where's the 0?
At the center.
No, there's no, it's a 0-point energy, isn't it? So it doesn't actually touch. What's the
So
level
zero
down?
is the
Is it what-
initial and the final. Final minus initial.
Because there is a 0 on here. There is a displacement of 0.
It's the speed of 0. It's not moving. It's changing.
Okay, you're talking about speed. The displacement at 0. Think of that hanging spring. That's the easiest one. Because you can think about a carbon triple bond or whatever, fine. But just think of a hanging spring. It's easier. And plus, you've seen it. So you have the hanging spring, and you don't pull down on it or anything. It's just hanging at its what position? Starts with an E. Equilibrium position. That's where the displacement is 0. Okay. But there's no vibration going on, so that doesn't do any good. So you got to get the thing vibrating. So you pull it down, you get the thing vibrating. Okay? Okay, keep going, Mel. That's how you get displacement.
Right. So as it moves, you have positive displacement and negative displacement.
Mm-hmm.
And these are going on forever and ever and ever.
Yes. So what does that mean? That this, no matter what the displacement is, you always have a potential energy for it. hard to imagine. Just like having that hanging spring here, and I can pull it down as bloody far as I want, not have to be really strong. Probably Al and I would have to hang on it, right? And we're pulling it down farther. We can pull it as far as we want. Get the thing to vibrate. We can never damage the spring. We can never break the spring. But we're not talking about springs. We're supposed to be talking about molecules. In other words, what cannot happen starts with a D.
Dissociation.
Exactly. Dissociation cannot happen. It's impossible. Okay, so we're getting close. You're almost done with this.
This is harmonic.
This is called harmonic. Oh, good. That's another good insight. This is called harmonic motion. Exactly. Okay, that's good. But we haven't really finished this plot because there's not one plot on there. There's two. So what are they doing with this? Keep going, Mel.
Constant. Okay, that's a large force constant and a small force constant.
Okay, so what does that mean? What does that mean in terms of this spring that we have bouncing up and down here?
Amplitude's changing.
The large force constant one has a really tight spring. Right? And the small is the one that was much looser.
Does that make sense? She says that the red plot is for much looser. So the red plot has, it looks to me like a larger displacement. Larger amplitude vibration. Does that make sense? Yeah, that makes sense. Right. Which one would correspond with a higher frequency of vibration? Or are they the same? Or E, not enough information?
Same energy. Same frequency.
Same energy, same frequency.
Doesn't the larger K indicate the frequency increase?
What did you say?
A larger K indicates the frequency increase?
A larger K, larger frequency. You can do these calculations. You did them in the homework. It's right here. We just don't like using this word omega. We like using the word frequency. Fine, just put 2 pi nu in for the omega. So then it's not directly well, it's got the square root there, but they're both on top. So which one would have a higher frequency?
The blue one.
Higher K, higher frequency, exactly. So someone mentioned, this isn't quite in here, but I guess I could add it. There's nothing stopping me since I wrote the exam. I could add these little lines in here. Should they be equally spaced, or should they be getting closer and closer together? Do you remember this?
Equally spaced.
Equally spaced. Vibrational energy ladders are equally spaced, right? And as I'm going up this ladder, what's changing? Amplitude. Frequency? Can't. Frequency can't change, because look, omega is the square root of K over mu. The only way to change the frequency is to change the bloody spring, change the mass of what's vibrating, what's moving. Back to Al. What's going on here?
Okay, so D, oh my goodness, it's growling. DO is the bond dissociation energy.
Okay.
I don't know a lot about this.
Anyone else have anything? Is this plot the same as this guy?
No.
Are they trying to illustrate the same thing? Okay,
Harmonic.
okay, be careful though. Is this whole thing anharmonic?
No.
No.
Where is the harmonic part?
Or the
DO is this whole thing.
The back part of the
This right here.
the parabola part.
Oh, I see what you're saying. This guy. He looks kind of similar to that, yeah. But then look, this other side's messed up. So this is harmonic motion. So this whole, no, that, if you say this, well, you can't just say this one line. You have to talk about this whole plot. Because this is, remember, this is displacement. They just wanted to make a measure, you know, minus the equilibrium. Well, that's what they're doing here too, displacement. They should have just left it as the same. Where's the harmonic region? In other words, what geometric shape is this? So where does this look like a parabola?
Oh, at the bottom.
At the bottom. There's your harmonic. Just circle it. But stop your circle where it's not a parabola anymore. So I wouldn't go this high. That's not a parabola. I don't know, maybe somewhere down here, I guess. So this might be a reach with this plot, but it might be a question that could be attached to it. Is we talked about 3n minus 5 and 3n minus 6. This referred to what? Normal modes of vibration. Okay, so if you, and each vibration has a nice little plot like this. Each vibration does. So it seems to me theoretically you should be able to excite every single vibration individually without interacting with the other ones. And you can as long as you're in the harmonic region. Otherwise you can't. You're going to be exciting more than one vibrational mode. But only don't forget about the selection rules. We don't have any plots on those. Remember what had to be occurring for it to be IR active, what had to be occurring for there to be a, what were the other ones? Ramen, rotational. So those are the major ones. I mean, the other guys I can ask a few little questions on, but there's not a whole lot. We didn't spend very much time on these guys. There's our P branch and R branch. We talked about how it's kind of nice to have it when you go to the FTIR, this is what you see, but it's kind of nice to rotate it this way. Why was that?
Because of the energy is going up.
Yeah, the energy levels. Yeah, then it looks more like these little transitions that we're used to seeing. So these are the different energy levels. And the more intense, the more the population. So that's really odd. I think we covered pretty much everything. So there's only 2 problems, 70 points worth of concepts. I probably won't be your favorite person after this exam.
Doesn't care.
Smith had fun writing the test. Hopefully you guys will have fun taking it.
Guarantee is the 20 points. What are the 2 problems you could?
Right, yeah, I can 2 force constant problems. I can do that.
The problems aren't that bad. Right?
Yeah, that.
Well, like, I'm not going to give you a slope one. There's no way. I have to give you a plot and everything.
Yeah, you could be saying that and then just go add it on before Monday.
No, I can't because I'm done. I have to go through it.